Okay, so now if we look at question 6.4.2.4, we're given this differential equation dw by dv is equal to minus nRT over v. You'll see in your thermodynamics where this comes from, but it's essentially from the ideal gas law. And we're looking at the work done in expansion of an ideal gas. But from a maths point of view, we just need to worry about being able to mathematically solve it. And so we're given this equation, dw by dv is equal to minus nRT over v, and we're given some limits. So when v is equal to vi, the vi stands for initial volume, then w is equal to 0. The work done is 0. So we're saying that it's we haven't got any work done in our system before we do anything. When v is equal to vf, w is equal to w, so w is our work done. And so it's the difference between the initial and final. So here, the first thing I need to do with any of these things is to collect like terms together. So there are no w's other than the dw, so that makes one side easy. So dw is equal to minus nRT, and I'm just going to split out my 1 over v here just to be really clear, dv. And I'm putting this in speech marks because at the moment it's not quite mathematically correct until I integrate it. So the next thing I'm going to do is going to put on my integration signs. And now this makes everything lovely and normal. And because my nRT are just constants, I'm having them outside my integration. It doesn't matter if they're in. For me, it makes my life a little bit simpler to see what I'm integrating, but it doesn't matter whether they're in or out of the integration sign. So now I've got my integration signs, I apply my limits. And as I've said before, it doesn't matter where you pair your limits, as long as you make sure that that they belong together. Because if we put them the wrong way up, we'll just end up with everything working out. We'll end up with two minuses, and overall it will be the same. But what we should do is we should put our lower limit on. So here this is between 0 and w. And then on my volume side, this is between vi on the bottom and vf on the top. So now I can integrate each side in turn. So if I integrate dw, it's essentially saying I'm integrating 1 with respect to w. And so 1 would just become w between 0 and w. Now remember, I don't need to worry about a constant of integration in definite integrals because they would cancel out. So now I have my other side and I have minus nRT, just some constants, they stay the same, and I worry about what happens in my integral. And as with a lot of things in chemistry, this is integrating 1 over v with respect to v. We see a lot of 1 over integration in chemistry. And so if I integrate 1 over v, that's the one that breaks the standard set of rules for polynomials. And this leaves me with the log of v between vi and vf. So now if I substitute in my values, I end up with w minus 0 is equal to minus nRT, and then I have the log of vf minus the log of vi. And just to tidy this up, getting rid of that w minus 0, that is just w. This is minus nRT log vf over vi. And you will have seen this equation in my thermodynamics course. So just following the same set of rules as we normally would, we have collected like terms together. We've integrated each one in turn. We don't need to worry about constants of integration because they will cancel out in definite integration. And we substitute in our limits. If we do each of those steps in turn, we should hopefully always end up with the right answer, assuming that our integration is correct.